Hanna SHIN from KGSEA Math Circle, and I'll be talking to you about deriving rotational motion from linear motion. So once we transition from linear motion, like projectile motion, velocity, displacement, and all those different concepts, to rotational motion like kinetic energy, inertia, angular momentum, and torque, which are the topics we'll be covering today, mechanical physics starts to get a bit complicated. Or so we think, because in reality, rotational motion is really no different from linear motion. If we take a closer look at where the formulas of rotational motion are coming from, we can see that rotational motion and linear motion are parallel in many ways. And when we realize the symmetry, rotational motion becomes just as simple as linear motion. So hopefully today's topic will be helpful to those who have already learned about rotational motion in physics, but are confused, or just those who want to know where these formulas of rotational motion are coming from. So let's just start off slow and easy with the coordinate system. The coordinate system is the space where we can express the location and movement of objects or points. The coordinate system is convenient because it converts objects in space into numbers, so that later we can take mathematical operations on the numbers to predict or describe the objects in motion. And that's essentially what mechanical physics is. It's a branch of physics dealing with objects in motion and how its trajectory changes when a force is applied to the object. So in linear motion, we use the Cartesian coordinate system. And in rotational motion, we usually use the polar coordinate system. In order to go from the polar coordinate system to the Cartesian system, we use the formulas that we're already familiar with. So x equals r cosine theta, y equals r sine theta. We'll go into this more later because first we have to talk about something. And that is vectors and scalars. As we know, vectors are essentially just arrows that show the direction and the magnitude of an object in a space. When we're deriving rotational motion from linear motion, we'll be using vectors all the time. So just note that in this video, if you see like a variable with an arrow on top, that would be a vector, and anything else without an arrow, that would be a scalar. Before we move on, let's actually note some of the formulas of linear motion and rotational motion. Note that many of the formulas here on the table are parallel to each other. So if we note this equation here, we can see that x and theta are symmetrical, v and omega are symmetrical, and a and alpha are symmetrical. So the thing that connects linear motion and rotational motion is actually just r radius. So we can see where this is coming from. If I just try to draw a circle, here's a nice circle, and we want to find the arc length of a circle. So that's r, this is theta, s is arc length. If we want to find arc length, we know that we just need to do r times theta, right? So this is a formula we're already familiar with. And s here is actually just the same thing as x. We want to find the distance from this point to this point. So s is just x. And the role of r here is pretty much the same for position, velocity, and acceleration, hence why we have these equations here. So keep this relationship in mind. If we want to go from angular motion to linear motion, all we have to do is multiply angular motion by r. And this is the most crucial relationship when deriving rotational motion from linear motion. Angular motion is linear motion in the presence of r. So now that we've understood this simple relationship, let's actually see how to derive rotational motion. We won't be going over uniform circular motion and centripetal motion because if we want to derive these equations, all we have to do is some basic algebra and differentiation. And we also will be going over rotational inertia around an axis because the process of deriving these formulas is repetitive. And so I think that's a topic for another time. But we'll be looking at these topics here because they're a bit more complex. And so hopefully this video will be more in line with some of your needs. So starting with rotational kinetic energy. Now we're dealing with objects called 3D rigid bodies. Rigid bodies are essentially just a solid object that doesn't change shape. I'll draw a rigid body here. So here's a blob, and this rigid solid body is made up of tiny masses, right? These are my masses, and the distance between two particles in this rigid body, let's say this one and this one, are constant. They don't change, even when a force is applied to the object. That's the definition of a rigid body. And here, this vertical line is the axis of rotation. Now, if this axis of rotation, let's say, rotates this way, the rigid body as a whole also rotates the same way. Now, this scenario is really no different from situations that we're already familiar with, and that's circular motion. So instead of looking at this rigid body from the side, if we decide to look at this rigid body from the top, so like this, then we can see that actually the movement of the particles is the same as circular motion. So mass here would be going this way as this axis of rotation is also spinning around. All right, so now let's go into the actual derivation of rotational kinetic energy. We know this, we know that kinetic energy of just one particle is 1/2 mv squared. But when we're dealing with rigid bodies made up of many masses, I'll draw my mass one more time, just for reference. Here's my masses. And this rigid body is rotating around the axis. We want to calculate the total kinetic energy. And to do that, all we have to do is basically just add up the kinetic energies of all these tiny masses in the rigid body. So that means that total kinetic energy is the sum from particle I to n, k, of all the masses. So if we just use the formula that we're already familiar with, that would be now from here, we know that V equals R times omega. We saw that in the previous slide. V equals R times omega. So let's write that out as well. M of I times R squared times V. Oh, sorry, that is omega squared. And from here, we can actually take out the omega because we know that omega stays constant. If an axis of rotation rotates, one period, then that means all of the masses are traveling the same distance. That's just 2 pi radians. So we can move out omega, and that gives us let's also move out. Okay. Okay, there we go. Let's also move out 1/2 because we know that that's also constant. Okay, and so this formula that we have here is actually pretty parallel to what we already know. K equals 1/2 mv squared. 1/2 here is corresponding to the 1/2 that we see in the equation K. Omega is corresponding to V, that makes this this thing here corresponding to M. And we actually have a name for this, and that is denoted as I. That is just rotational inertia. So we can see that rotational inertia comes from us trying to calculate rotational kinetic energy. Okay, so let's just simplify everything. In conclusion, total kinetic energy or rotational kinetic energy is 1/2 I omega squared. So that's why we have this formula of rotational kinetic energy and this formula of rotational inertia, the sum of m times r squared of all the particles in this rigid body. Okay, so now let's get into the meat of this video. Angular momentum and torque, which will be the topic after this slide. Recall the most crucial relationship we know about linear motion and rotational motion. Rotational motion is linear motion in the presence of r. And because we know that momentum is denoted as P equals mv, we can just multiply r to get angular momentum. So angular momentum is denoted as L. That would be just momentum, mv, times r. Now, this is a scalar quantity. So we want to find the vector quantity, and we need to convert the scalar quantity into a vector. So, we're just going to do the same thing. R radius cross E momentum. And so let's see where this equation we have here is coming from. I'm just going to draw angular momentum for you. So let's say that we have a mass here, and it's rotating. This is M. This is R. This is the tangential velocity or linear velocity V. And we know that P equals mv, so that just means that the direction of V here is the same as the direction of P. So I'm just gonna write that here for our reference. And because R and P are perpendicular to each other, we know that we have to cross these two quantities. Angular momentum is L. But in cross products, we need to make sure that the orders aren't mixed up. We need to check that angular momentum L is equal to R cross P, not P cross R. And so to do that, we just need to use the right-hand rule. L is the direction of angular momentum, and so that would be pointing up. That would be our thumb. And because if we just move P onto the origin, just like R, we would go from R to P. And in that way, your thumb, your angular momentum is pointing upwards, the same direction. So here we know that L equals R cross P, not P cross R. Okay, so now let's look at angular momentum in the context of a rotating rigid body. I'll just draw the same rigid body that we've been using throughout this video. So if this rigid body is rotating, we want to calculate the angular momentums of all the different masses. So we just add up the angular momentums. So L total is just the sum of everything. And we know that L is R cross P, so let's write that out as well. Okay. Now here we know that Okay, now let's just convert linear momentum. So P is we know that it's mv. Now we have v in the vector form. We know that v is our omega, but this is again a scalar value. So we need to convert v into a vector form. So let's just look at where this is going. If we have the same mass, r radius, and v, and if this is the direction of omega or angular velocity, then in order to get v, our thumb is facing ahead of us, outwards, we need to go from omega to r, not r to omega. So we're going to cross omega with r. So v equals omega cross r. So now let's just continue with our equation. Omega cross r. And because mass is just constant, we can also move that out. Mi times r cross omega cross r. And if we just solve this out using basic math, and that would just be m of r dot omega minus r dot omega dot r. Okay, so there we go. Now, recall that when we have two vectors and we're doing the dot product of these two vectors, we want to use we want to multiply the two magnitudes of both of the vectors times cosine theta. So let's take a look at both of these components of this equation. So r dot omega would just be r omega cosine theta, but we know that the direction or the angle between r and omega here is 90 degrees. So that just makes cosine 90 0. So this entire part here is just 0. So that's simple. And we want to do the same thing for this part. That would just be r cosine theta. Theta is 0. So this component here would be r squared. So let's write that out. R squared omega. There we go. And from our previous derivations of rotational kinetic energy, we know this. We have learned that this is moment of inertia or rotational inertia. So that means that angular momentum in conclusion is I omega. And we can see that this I omega here is parallel to what we already know about momentum. So I is just parallel to m, and omega is parallel to v. So here we see this parallel going on. So here are our two equations of angular momentum. And finally, let's look at torque. Torque is basically rotational force, and that's the definition of torque. So that means that we want to do R cross F. And once again, if torque is in the upward direction, the positive Z direction, and we use right-hand rule, then we would do R cross F, not F cross R. So let's just write that out. Torque tau equals R cross F. Now, because we've already established that torque is parallel to force, and we know that force, another definition of force is dp dt, change in momentum. We can actually use our understanding of momentum and to find another equation for torque. So torque is actually just dl dt. So we're going from this linear motion to rotational motion. That's angular momentum. And because we know here that L is I omega, I is just constant, so we're gonna bring that out. D omega dt. And we know that d omega dt is just change in angular velocity, and that's just angular acceleration. So let's also write that denoted as alpha. So now we have torque is R cross F, but it's also torque equals I omega. That's rotational inertia times angular acceleration. And just like how angular momentum is parallel to linear momentum, torque is also parallel to force. So this should look somewhat familiar because we know that torque is I alpha. Torque is parallel to F, and F equals ma. We can see this parallel once again. So torque and F are parallel. I and M, and alpha and A. And this is, the most important formula in mechanical physics. It's Newton's second law. So torque equals IA would also mean that this equation is Newton's second law in rotation. No motion of a rigid body. So that's why we have these following equations. And that concludes deriving rotational motion from rotational kinetic energy, angular moment of inertia, rotational inertia, angular momentum, and torque. Deriving these equations from a motion of a single point. I hope that this video has helped understand that rotational motion is really similar to the concepts of motion that we're already familiar with. Thank you very much.